Next set of formulas, relationships, call them what you like, we're going to look at is what's known as the double angle formulas. We're going to create them using the ones we saw on Friday. So sine 2 theta, so double the angle theta. Well, I could rewrite 2 theta as theta plus theta, and then use sine cos cos sine. If it's a sine, it's a sine. But when I look at these, sine theta cos theta and cos theta sine theta, well, it's the same thing. The order that you multiply, it doesn't matter. So I could rewrite that as just simply 2 sine theta cos theta. So that's our relationship for sine 2 theta. So for cos 2 theta, same idea. Cos cos sine sine. If it's not the sine, it's not the sine. But cos times cos is cos squared. Sine times sine is sine squared. So we have cos squared minus sine squared. We could, of course, write this another way, because I could change the sine squared to 1 minus cos squared, because if you remember, sine squared plus cos squared is equal to 1, and I get 2 cos squared theta minus 1. The advantage of that is we're only dealing with one ratio there, just cos theta, rather than having 2. But of course I could have rewritten the cos squared. The cos squared is 1 minus sine squared, and we get 1 minus 2 sine squared theta. So there's 3 different ways we could do cos 2 theta. I guess it just depends on what information we have as to which one we would use. Okay, well let's do tan. So we get tan plus tan, or 1 minus tan tan. So on the top of the fraction we end up with 2 tan theta. On the bottom of the fraction, 1 minus tan squared theta. It's better to think of them as double angle formulas rather than 2 theta, because it's just double. So I could create one for 10 theta, or 8 theta, or double anything. So sine 2 theta, 2 sine theta cos theta, cos 2 theta, cos squared minus sine squared, which we could rewrite as 2 cos squared minus 1. Another advantage of that is I could rearrange that formula and make cos squared the subject. This will become very useful next year when we're looking at integrating trig functions. So it gives us an easier way of integrating cos squared with sine squared. So 1 minus 2 sine squared, I could rewrite that one to make sine squared the subject. And again, that will help us out next year when we're integrating trig. And there's our tan 2 theta. So 2 tan theta on 1 minus tan squared theta. Right, some examples. The first example we got here, if cos theta is 2 thirds, find tan 2 theta. Well, I'm going to have to draw myself up a triangle, because they've told me cos theta is 2 thirds. But the tan 2 theta formula, I need the tan ratio. So the first thing I do, work out the other side is the square root of 5. I can now sub into our formula, because I can read off my triangle. Tan theta is, what's that going to be? Root 5 on 2. So substitute that in, tidying it all up. Eventually, there we go. We end up with minus 4 root 5 for that one. Find the exact value of sine 5 pi and 12 cos 5 pi and 12. When I think about all the different formulas, sine cos. So sine cos, well, that's half of 2 sine cos. And 2 sine cos was the formula for sine 2 theta. So what I have there is the sine of double 5 pi on 12, which is 5 pi on 6. That's one of our exact ones, 5 pi on 6. It's in the second quadrant. Sine's positive. The acute angle is pi on 6, and I always go back to the degrees in my head for some reason. So sine 30 is a half. So we get half times a half, a quarter. If cos theta is 2 thirds, find the exact value of sine theta on 2. So again, this is where it's useful to think of it as double angles, because theta is double theta on 2. I'll use that rearrangement that we saw with sine squared, because that will allow me to substitute in the double angle. So cos theta, theta is double theta on 2. And I get sine theta in terms of cos 2 theta. Just highlighting that, if I sub in, I'm just saying they're double angles. So instead of theta, I've got half theta, which means instead of 2 theta, I've got theta, double the theta on 2. Let's substitute in our cos theta, and I end up with that sine squared is 1 on 6. There's 2 possible answers. So unless I have more information, I don't know whether it's going to be positive 1 on root 6 or negative 1 on root 6. You see, they've told me cos theta is 2 thirds. Perhaps that was in the fourth quadrant. And so when I halved it, I ended up with something that's in the... Oh, that'd still be positive though. Oh, what could it have been? Maybe I've gone round twice. So then when I've halved it, I've ended up in one of the quadrants where where sine was negative. But unless I know that, I don't know for sure. So best I can do is plus or minus 1 on root 6. Okay, let's prove this one. The square root of 1 minus cos 2x on 1 plus 2 cos x is going to be the same as tan x. I'll start with the left-hand side for this one. Cos 2x, I had 3 different ones I could substitute in. But looking at what I'm trying to prove, I'm trying to prove tan x. And tan I know is sine on cos. So for the top one, it makes sense to use the one that had sine in it. So I'll use 1 minus 2 sine squared. Whereas the bottom one, it makes sense to use the one that has cos in it. The 2 cos squared minus 1. Tidying that up, it comes out quite nicely. Because the top of the fraction, 2 sine squared. Bottom of the fraction, 2 cos squared. The 2's are going to cancel, and I've got the square root of tan squared, but the square root of square cancels out, and I've got the tan x that I wanted. This one comes from, well, quite a long time ago now, an HSC question. But it illustrates a question which can be done easier if you remember your double angle results. See, what I've got here, we've got to prove that this is equal to 2. So there's the fraction. Algebraic fraction, let's pull it into one fraction. And I get that pattern, sine, cos, cos, sine on the top of the fraction. Now what a lot of people did that particular year, instead of doing it like that, they looked at sine 3 theta and said, oh, let's create a formula for sine 3 theta. And wrote it as 2 theta plus theta, and went sine, cos, cos, sine. It worked, but it was a lot longer. If we combine it as one fraction and notice the pattern on the top, so sine, cos, cos, sine, so that must have been the sine of 3 theta minus theta. You'll also notice I've multiplied top and bottom by 2. Why did I do that? Because 2 sine theta cos theta would become sine 2 theta. And sine 3 theta minus theta is also sine 2 theta. I can cancel the sine 2 thetas and I'm left with the 2 that they wanted me to prove. So it only took me 1, 2, 3 lines, whereas doing it the other way would have taken several more lines. An even older one, we had to prove this identity. 2 tan theta on 1 plus tan squared. Very tempting to go, oh, that's tan 2. But it's not, because the tan 2 theta formula had 1 minus tan squared on the bottom. We have to show it's actually sine 2. So all right, again, I'll start with the left-hand side. I want to end up with sine. So I think what I should do here is convert all of those tans into sine on cos. And that'll bring out sines and cosine ratios. All right, well, we want to make the denominator of these all the same. Let's multiply everything by cos squared. And that'll get rid of the fractions on a fraction situation. So the top will become 2 sine cos. The bottom is cos squared plus sine squared. But we know cos squared plus sine squared is 1. And the top of the fraction, 2 sine cos, yeah, that is sine 2a. So we have our answer. So the sine of 2 times the inverse cos of 3/5. Remember, inverse cos is representing an angle. So this is still saying double angle. So my formula is 2 sine theta. Now, well, let's actually make it theta to make it more obvious. So we're saying theta is representing this angle, the inverse cos of 3/5. Draw myself up a triangle. Adjacent over hypotenuse, the other side is 4. So now I'm just saying, oh, what's 2 sine theta cos theta? So it's a double angle result. Read off my triangle, and I've got 24 and 25. The second one's going the other way around. It's an inverse cos to start off with. So inverse cos of twice cos pi on 3. Well, hang on, cos pi on 3 is an exact value. So let's just sub that in. Cos of pi on 3, well, pi on 3 is 60 degrees. Cos 60 is a half. 2 times a half is 1. So it's just saying, what's the inverse cos of 1? Oh, it's 0. So 17e, let's play with our double angle.